So we know that the inverse of a scalar a is 1 by a, because if we multiply a with 1 by a, we get 1. It would be nice to have something similar for matrices too. So the inverse of a matrix is the same idea. Alright, so the inverse of a matrix is denoted by A inverse, and if we multiply A with A inverse, we get the identity matrix. Okay, so let me actually formally define what is matrix inverse. So we say that A is invertible, and this is synonymous to saying that A has an inverse, or A has an inverse. All right, if there exists another matrix B. All right, if there exists another matrix B such that A into B is equal to I, the identity matrix, and so both these conditions need to be true, and B into A is equal to I. All right, so then the matrix B is the inverse of A, and it's written as A inverse. Okay, also you need to remember that all invertible matrices are always square. So square matrices are the ones that have same number of rows and columns. Okay. So there are two quick things that I want to cover before I move along here. So first important thing is that inverses are unique. So inverses are unique, and we can prove this result by contradiction. So let's say A has got two inverses, B and C. Okay, so then by definition A into B is equal to I, and B into A is equal to I, right? Also, since C is an inverse of A, so A into C is equal to I, and C into A is also equal to I, and this is by definition. All right, so now let's consider the product BAC, okay, which can be simplified as B times A into C. And remember that matrix products are associative, so we can do this. So BAC can be written as B times the product of A and C, and A and C is 1, right? A multiplied by C is 1, so this simplifies to B into I, which simplifies to further B. Okay, and similarly BAC can also be written as BA, the product of it, and multiply it with C, again using the fact that matrix multiplication is associative, and B into A is I, so this becomes I into C, which further simplifies to C. All right, and compare these two equations, you will see that B is equal to C. Okay, all right, so that's the first thing I wanted to talk about. And the second thing I wanted to talk about is the fact that since matrix multiplication is not commutative, so we never write A inverse as 1 by A. So we never do this. And this becomes clear, right? Because if you start using this notation, then AB by C is very ambiguous, right? So I mean, how do you actually simplify this? Is it 1 by C into AB, or is it, let's say, 8A into B multiplied by 1 by C, right? So all sorts of ambiguity crop up. So that's why A inverse is always written like this and never like this. Okay, with that said, let's try to calculate the let's try to calculate the inverse of a matrix, and let's do it for a 2 by 2 matrix. Okay, so let's say A be a 2 by 2 matrix, which is, let's say, A, B, C, D, and A, B, C, D are scalars. Then the inverse of A, that is A inverse, will be equal to 1 by AD minus BC. So this scalar, this guy, multiplied by D minus B minus C and A. Okay, so in other words, what we really have done is that we have swapped the diagonal terms here. So A and D have been swapped, okay, to get D and A over here, and then we added a negative sign in front of B and C. So we did negative, added negative sign in terms of in front of B and C to get this matrix, and then we multiplied this matrix with 1 by AD minus BC. And if you remember from our last unit, AD minus BC, this is the determinant of a 2 by 2 matrix, right? So this simplifies to 1 by determinant of A, right, and multiply it with D A and minus C minus B. Okay, so let's take an example to make things more clear here. So let's say, okay, let's take a simple example. So let's say A is, let's say, 1, 2, 3, 4. Okay, and we need to find A inverse. Okay, so we find A inverse by, first of all, what we need to do is we need to swap these two elements. Okay, so this becomes, so this has so once you swap these two elements, right, 4 comes here, 1 comes here, and then you add a negative in front of 2 and 3, so this becomes minus 2 minus 3. Okay, and you multiply this by the determinant of A, and you can actually see the determinant of A is minus 2. So you multiply this by minus 2, and then you can further simplify this. So this becomes 4 by minus 2, minus 2 by minus 2, minus 3 by minus 2, and 1 by minus 2. And this further simplifies to minus 2, 1, minus 3 by 2, and minus 1 by 2. Okay, I'm sorry, this will be plus 3 by 2. Okay, and you can, you can actually, calculate this yourself. So you can multiply A and A inverse, and you will see that you will get the identity matrix. And you can also multiply A inverse by A, and you will further again get the identity matrix. So in this actually I've shown you how to calculate the inverse of only a 2 by 2 matrix. So later on in this course, we will see how to calculate the inverse of a higher dimension square matrix. Okay, so now moving along. So again, going back to the definition, right? So if B is an inverse of A, so if B is an inverse of A, then A into B has to be equal to I, and also B into A has to be equal to I, right? So these two equations mean that B is inverse of A and also A is inverse of B, right? So let me prove it to you, right? And I'll tell you why this is the case. So let's say X is B inverse. Okay, so let's say X be a matrix and it's the inverse of B. So then we have that B into X has to be equal to I, and X into B also has to be equal to I, right? So now if we compare this and this equation and this equation, me change the color. So if you compare this equation and this equation, and if you compare this equation and this equation, and basically use the result that the inverse of a matrix is unique, we will arrive at the conclusion that B inverse is actually equal to A. So that means that A and B are inverses of each other. So if A inverse is equal to B, then implies and implied by that B inverse is also equal to A. And this also means that A inverse and inverse of this will be equal to A. So till now we have dealt with inverses, but really, why do we need them? So we need them to solve matrix equations. So for example, say x, a and b are scalars where a and b are known quantities, and let's say you had this equation x into a is equal to b, and if you had to find out x, how do you do that, right? You can find out x by multiplying 1 by a or a inverse on RHS and LHS. So we will do a times 1 by a is equal to b times 1 by a, and this simplifies as x is equal to b by a. Okay, but now assume that, let's say, a, b and x are not scalars but they are matrices. So let's say x times a is equal to b, where x, a and b are matrices, and we want to find out what is the matrix X, right? So it would be nice to again divide both sides by A, but remember we cannot actually get X like this, right? X is equal to B by A, right? We cannot divide it like this. But what if we multiply by A inverse on both the sides, right? So X A, and if we multiply this by A inverse on LHS and RHS, so this simplifies as A into A inverse becomes I, so this becomes XI is equal to BA inverse, and this is again X times I would be X, and this becomes X is equal to BA inverse. Okay, so now we have our solution, assuming that we can calculate A inverse. All right, so let's take another example. So let's say if we were trying to find out, if we had this equation ax is equal to b, and we wanted to find out x from here, and remember that this example is different from this example. All right, because x is now after a. So with matrices, the order of multiplication usually changes the answer, right? So we know that matrix multiplications are not commutative. So A into B is not equal to B into A. Okay, it's almost never true. So how do we solve this equation? So using the same method, but we put A inverse now in front. So we multiply A inverse in front in both LHS and RHS. So this becomes A inverse AX is equal to A inverse B, and A times A inverse becomes I. So I into X is equal to A inverse B, and I into X is simply X, so X is equal to A inverse B. And you can see that the answer is different, right? So X is A inverse B here, and in this case we found the answer as X is equal to B times A inverse So alright, so I'll see you folks in the next lecture, where we will talk about the properties of matrix transpose and inverse.